Right, so thank you everyone for coming. Apologies for the delay. Yeah, this all worked in the staging environments, didn't work in production apparently, such as life. That I will try to make up some time here, so I'm gonna cut out my good jokes and just leave the bad ones. I figure that's the better strategy here. My name is Larry Garfield. You may know me online as Krell. If you want to make fun of me on Twitter during this talk, that's where you do so. I generally encourage it. You can also make fun of me in Slack as well. That's fine too. I am the Director of Developer Experience at Platform SH. We're a continuous deployment cloud hosting company. For those PHP people in the room, I'm a member of the PHP Fig Core Committee, and I do implement PSR 8. If you're not a PHP person, you probably won't get that joke. If you are a PHP person, you ought to get that joke. If you don't get that joke, ask me later. These slides will also be online shortly after the talk, and I will post a link to them in Slack as well. So this is a computer. This is a very old computer. Specifically, it is an IBM System 360 Model 20. These were first announced in 1964. And System 360 was slated to be the world's first complete range of compatible computers. That is, multiple models of computer that could run the same software. And in 1964, this was a very big idea. This was cool and new, that you actually could run software on multiple systems. And that required, for the first time, a distinction between architecture and implementation. Prior to this, the exact hardware itself was the architecture and the design and the implementation all in one, but this required splitting it up into pieces, which had a number of advantages. For example, it meant you could write software that was compatible both with your standard reel-to-reel storage, which everyone was using at the time, and this really cool, newfangled, crazy idea called a spinning magnetic disk for storage, that in something the size of a refrigerator could store thousands of bits of information. And this was phenomenal for the 60s. So, a lot of benefits to this architecture. System 360 ended up being one of the most important and influential computer systems in history, and its legacy is still with us today. For example, System 360 is the first system that defined a byte to be 8 bits in size. Did you ever wonder why a byte is 8 bits in size? Because System 360 said so. In fact, before that, it was common for different systems to have different size bytes. The most common was a 6-bit byte, which had the downside that it didn't have enough characters, therefore, in its character table to handle both uppercase and lowercase letters. So a team of researchers looked at this and said, all right, so if we're only going to have uppercase or lowercase letters in our system, all right, so this is a System 360. This is spinning this computer. This is the legacy of System 360. 8-bit bytes. Moving on. 6-bit bytes were the common standard before that, and a team of researchers asked, all right, so which of these is if we can only have uppercase or lowercase slides or characters, then which is better? And so researchers did the work and figured out that in English, lowercase letters are more readable than all uppercase letters because you get more variation in letter height, so it's easier to distinguish. And they took this conclusion to their boss, and their boss said, but we're IBM, we can't have our name in lowercase. And so for the next 30 years, the convention was to use all uppercase characters, even though that was in fact worse for readability, such as technology. But System 360 had an 8-bit byte. It also introduced the idea of byte addressable memory. Before this, many systems would let you access memory by a bit address or bit offset rather than just at the byte level. System 360 was the first one that did at the byte level, which now everything does these days. It also introduced the character encoding system called EBCDIC, which you probably have not heard of because everyone used ASCII instead because it was way better, and these days we're all using Unicode. So, okay, not everything it did is still with us. System 360 still lives on today. as the IBM Z series of mainframe. These are still backward compatible for many programs written for the System 360 in the late 1960s. May your code live as long. The lead team for System 360 was these two people, Gene Amdahl, who was the lead architect for the system, and Fred Brooks, who was the lead manager for it. Brooks is actually the person who coined the term computer architecture to refer to what Gene was doing. After the project was over, the team went their different ways, and many of them ended up in academia, like you do. And many years later, Brooks wrote a book called The Mythical Man-month, in which he looked at the development of System 360 as well as academic research that had been done in the intervening decade to say, all right, what are some lessons learned from this? How does one manage large-scale software projects effectively and not screw up in all the ways that we did on our project? Because of course it didn't go according to plan, nothing ever does. And in 1995, he released an anniversary edition, that's what you see here, that includes a couple new chapters and revisits the original book just to say, all right, this is what I said in the 70s, it's now the 90s, is this still true? And his overall conclusion was, yeah, most of this still applies because technology changes, humans don't, and humans are the important factor here. And it's now been another 20 some odd years after that, it's up to 25 years now. What I'd like to do with this morning is look back and ask the same question. 45 years on, is it still valid? And I think the argument is yes. So I'm going to follow a different outline here than Brooks does, but I'm pulling out the major ideas. One thing that he does not get right is the book uses male pronouns exclusively, even when it linguistically isn't necessary. So ignore that part. There's actually nothing gendered in here in anything we're talking about. I'm also going to pick on a couple of open source projects over the course of this talk, and please don't take offense. They're projects I've worked on, so I can get away with it. I'm just using them as examples. You can put in any number of projects here if you wanted to. First up, you may have heard of Brooks' Law before. Adding people to a late software project makes it later. I'm sure most people have heard of this at some point. If not, well, you've heard it now. Why is this? Why is it that adding people to a late project makes it later? Well, fundamentally, it's because communication is hard. Communication is very hard. Why is it hard? Because it does not grow linearly. If you have two people collaborating, you have one point of contact, one interface, one line of communication to keep track of. If you have three people working together, you have 3 lines of communication to keep track of. If you have 5 people, you have 10 lines of communication, and so on. There's even a nice, clear mathematical formula for this, which you do not need to memorize at all. It's called combinatorics, which, takeaway here, the more people you add, the more lines of communication you add, faster than the number of people. And more communication means more overhead of just making sure that everyone is on the same page. Part of the problem is that tasks are not parallelizable. This is a Dilbert, this is a management talk, so I have to have a Dilbert reference. I heard all of you because this project will take 300 person days to complete. So there are 300 of you. I want you finished by 5 o'clock and clean out all your desks. You're fired. This clearly is not how it actually works for many reasons. Partially, it's just the overhead of coordinating 500 people or 300 people eats up most of your time. This is true even for unskilled tasks. Why? Because resources are limited. You have communication, you have different skill levels. Years ago, where this thing goes to, I was helping friends move from Chicago to New York, and so we're helping them pack up their apartment. And they had, say, 100 boxes they needed to put into a moving van. So the smart answer, therefore, is, all right, let's get 100 friends together. Everyone carries 1 box, we'll be done in 30 seconds. Clearly, that doesn't work. Not because they didn't have 100 friends, they did. But we only have 1 elevator. We only have 2 dollies. there's only so much packing tape. There's doors that only fit one person at a time. The people who are packing the van need to also be the people unpacking it at the other end, so they know which boxes are fragile and which ones are stacked on top of what. Even in a very basic unskilled task, the tasks are not completely parallelizable. We did eventually get them moved and packed up, and really the only question that remained there was why anyone would want to move from Chicago to New York. But I don't know, that's another question. I guess I'm talking to people from Indiana, this joke should work, I hope. People and months are interchangeable commodities only when a task can be partitioned among many workers with no communication among them. No communication among them. If the different workers have to coordinate at all, then the value of adding more people is lower than the value of a single person. The more people you add, the more overhead you create. And adding people, especially late, incurs cost. Or Gilbert, of course. How long will your project take if I add 2 more people? Well, add 1 month for training, add 1 month for extra complexity, and 1 more month to deal with their drama, because people are going to be people. Adding people makes things worse half the time, unless you add it early enough. How early? It really depends on the number of swim lanes. The earlier you put people on a project, the earlier they can dig in and get acculturated and understand all the nooks and crannies and the campfire knowledge of the project. Swim lanes is a concept from Agile. It roughly translates to the number of parallel tasks that can be worked on at the same time without bumping into each other. Different projects have different natural swim lanes. Some projects may have 3 natural swim lanes. Any more than that, and you're going to spend more time fighting with Git conflicts than you are anything else. Other projects may be 5 or 6, or sometimes just 1. Many projects will only have a single reasonable swim lane for a given component. Putting more than 1 person on it is going to make it worse, not better. The maximum number of developers you can have on a project, I would argue, is the number of swim lanes plus 1. That plus 1 is a buffer, so someone can be doing code review, someone can go on vacation, someone can get sick. And that's just talking about the developers, mind you. I'm not talking about the project managers and other non-coding people, non-developers. There's even math for this. This applies to technology too. It's called Amdahl's law. Amdahl is in the same gene Amdahl we talked about before. This is measuring the gives the theoretical speedup in latency of the execution of a task at fixed workload that can be expected of a system whose resources are improved. Roughly, if this is a measure of how many more resources you can throw at something before it no longer is giving you any benefit. In this case, it's looking at, this particular example is looking at the number of processors you can throw at a problem. And again, ignore the math, just know that there is math to it. You can see here, this red line, even if the project is 75% parallelizable, adding more than 64 processors, workers, units, whatever, is really not going to get you any benefit. If a project is 95% parallelizable, that's almost entirely parallelizable, then you can throw you can't throw more than about 1,000 CPUs at it, or it just doesn't give you any benefit. Then these numbers are a lot lower when you're talking about people. This is for CPUs. So what do you think? Still true? Does this ring true? This consistent with your experience? Yeah, it's consistent with mine, totally. So the first time I went to give this talk, actually, I was lamenting on Twitter that Mythical Man-month was such a good book, and there's so much material here. I could easily give 2 talks. There's 2 talks worth of material in this book. And so someone helpfully suggested I get a second speaker on stage to give both halves of the talk simultaneously. That way I can fit in twice as much material. Yeah, that's going to work. I'm hoping you're all laughing at home. I can't tell from here. That said, have you worked on any projects where the answer to not enough people or not enough resources or things are going too slowly is let's throw more warm bodies at it? I have. I was one of the lead developers for a long time. We did this all the time. How many people worked on Drupal 8? Over 5,000. That's a lot of lines of communication. That's a lot of overhead to slow things down. And this data is actually a year old now. What should we learn from this? Next thing Brooks talks about, why are estimates always wrong? Are you good at estimating? I'm not. Most people aren't. Why are estimates always wrong? Because you're estimating the wrong thing. When you give an estimate, you're estimating this piece up here in the top left, the program. That's just the program itself, but that's not the actual usable piece. The initial program is a prototype. If you actually want a programming product, something you can really use, then you need to take the effort to generalize the code, do testing, documentation, maintenance. All of this can take up to 3 times as much work as just doing the original skunkworks proof of concept program. If you want something that you can build on and extend, what you want is a programming system, which means you need to document and formalize your interfaces, work on system integration, make sure all the components fit together nicely. And that can take up to 3 times as much work as just the program itself. So if you want a full programming systems product, a generalized, well-tested, fleshed out, stable system with good interfaces, you're looking at 9 times as much work as just building that fast garage project proof of concept program itself. But your brain wants to estimate just that first part in the top left, not the full thing. So your estimates are going to be off by a factor of 9. That's a lot. Brooks also notes that a substantial bank of test cases exploring the input range and probing its boundaries must be prepared, run, and recorded. Translation: in 1975, automated testing was already an expected standard of behavior for engineers. Why are you not doing testing? Footnote: it's not that doing tests takes 3 times as long. Finding all of the bugs that testing will find for you, fixing all the bugs that testing finds for you, is what takes 3 times as long. The bugs are already there. Testing is what lets you find them and fix them. I also want you to ask yourself, how fast can you code? How many lines of code per hour can you produce? Whatever your answer just was, you're wrong, because I didn't give you enough information. Extrapolation of time from the 100-yard dash shows a man can run a mile in under 3 minutes. Still can't. The current world record is 3 minutes, 43 seconds. Why is this? Because it turns out, in studies, the amount of effort to add code to a code base goes up exponentially with the number of instructions already in the code base. It looks like this. The more program that already exists, the more work it is to add more code to it. Why? And this is true even if you don't have to coordinate with other people. Why is that? Because all of that code is still points of interaction. It's still more places you can have spooky action at a distance. It's internal interaction points within the code base. And no matter how clean you make your code, you still end up with the more code I add, the more possible knock-on effects it could have. And therefore, your rate of work goes down. There's also the limits of human memory. You can fit only so much code in your brain at one time to understand all the implications of a change. If what you're trying to do is the code base is bigger than what fits in your brain, you have to include the overhead of essentially swapping, disk swapping. Another test run by Joel Aaron found that productivity in large systems changed depending on the number of interactions within the code base. And I'm actually not sure if this research was interactions with people or code, but I think it's both actually. In a system with very few interactions, then you can produce 10,000 instructions per person per year. At the other end, if there's a lot of interaction, it goes down almost an order of magnitude. With a system with lots more interactions, you are almost 1/10 as effective, 1/10 as productive. Of course, what does a large mean here? 25 programmers and 30,000 instructions. That's not that big. That's actually a very large programming team and a very small code base. Of course, one thing to note, this study was done on assembly. None of us are writing in assembly, I hope. But follow-up studies found that PL1 followed the same curve. PL1 was the programming language popular in the 60s and 70s. It's kind of like the precursor of C, in a sense, as the industry standard language. But that same concept applied, just counting statements rather than counting CPU instructions, assembly instructions. What does this tell us? It tells us two things. One, more expressive languages that give us more power and capability per statement are in fact more productive because they let us get more done, more work accomplished in fewer lines of code, and therefore we can fit more into our brain. But that does not free us from this problem of the bigger the code base, the harder it is to evolve and maintain. What do you think? Still true? Yep, I'm going to say he's 2 for 2 at this point. Of course, we said a large program was 25 programmers and 30,000 instructions. How does that compare to the projects you've worked on? Who's worked on Symfony? 2,176 people. That's who. Anyone want to venture a guess how big the Symfony codebase is as of Symfony 4, not even Symfony 5? That's a lot more than 30,000. And that's not even one of the largest projects out there. What should we learn from this? Let's talk about planning. Let's talk about documentation, everyone's favorite topic. These two go hand in hand. Planning and documentation are the same thing. Brooks argues, in fact, that you need to write your documentation first before you write your implementation. Why? Because it turns out only when one writes do the gaps appear and the inconsistencies protrude. The act of writing turns out to require hundreds of mini decisions, and it is the existence of these that distinguishes clear, exact policies from fuzzy ones. I like to refer to this as rubber ducking with your word processor. I used to work as a consultant, building sites mostly for universities, museums, that kind of thing. And time again, the same pattern appeared. We'd go have an on-site with the client, and we'd talk for 3 days about everything they wanted to do and write down all kinds of notes and get a good picture. I'd go home, get back to the office, sit down to write it all up in a document format to verify, and come up with 500 other things that we didn't ask about. Things like, what happens if there's no data here? What happens if this piece is missing? What happens if this connection breaks? What does this button over here do that we didn't talk about? All of these things, when you have to write and describe them, come to the surface. You're going to have to make these decisions at some point. Better to make them explicitly rather than whoever happens to write the code that day makes a decision. The crucial task is to get the product defined. Many failures concern exactly those aspects that were never quite specified. Quite simply, if you don't know what you're building, you can't actually do a good job of building it. However, the manual, that written specification, is a necessary tool, but not a sufficient one. You can have a formal definition of what the system should do, and that's called code. It's very precise in describing what it does, but it's not very readable. It also misses the why. Documentation captures the why. Why are we doing it this way? Why are we doing this weird thing over here? Why do we convert this text from UTF-8 to ASCII and back to UTF-8? Yes, I've had to do that. Why? It's in the comments. It's in the documentation to explain why. In order to achieve this, Brooks calls for top-down design. Architect the system first at a high level, and refine that top-down to produce modules. Break the problem apart into pieces and solve those individually, and do that recursively until you have a good picture of your architecture. Then you can implement each module, debug and test each one of those modules separately in isolation, and put them back together, and definitely inform back up as needed. When you run into a problem, that should inform back up to the architecture and possibly let you modify that. basically we're describing your standard divide and conquer strategy, which is the basic strategy in, well, any science of any kind. Break a complex problem down into small, easy pieces, solve the easy pieces, and then put them back together. In fact, Brooks argues, you should just plan to throw one away. You will anyway. Again, you don't know what you don't know until you've built it wrong at least once. There's an old joke that you should never ship your version 1 release. This is why. There used to be a joke that Microsoft always took 3 versions of their system to get good because their first 2 were crap of any given application. That's true, but it's not because of Microsoft, it's because of software. Because you don't know what you don't know until you have realized you don't know it by trying to build it without knowing it. Now at this point, there's probably someone out there saying, but Larry, you just described waterfall. Isn't that terrible? We all know that's terrible. And actually, to his credit, in the updated version in 1995, Brooks said, yeah, okay, I did kind of describe waterfall there. All right, modify this a bit. Design top-down, but implement iteratively. First, build an end-to-end skeleton of the system. It doesn't need to do anything, it just needs to have all the pieces stubbed out that don't actually do anything useful. They're just placeholders, so that you have your overall architecture in place and make sure that that makes logical sense. Then always keep the system working. The system should always be able to compile, able to build, able to run. Maybe not usefully, but you always have an end-to-end working system that will at least compile or equivalent in your language. And then grow modules in place. Write individual pieces and plug them in, swapping out the stubbed out empty versions. Which means you can also throw out a module individually if you need to, replace it with some other components, refactor an individual piece, fine. What's this called? Refactoring. Refactoring is the art of throwing it away a little bit at a time. You're still throwing away your first version, but you're throwing away your first version in a controlled, managed fashion. So that you're never doing a full rewrite, you have a system that is designed to evolve with you. Now, bear in mind, this individual skeleton, this initial build, could take a while to make. This is not your first sprint gives you a skeleton. Building that baseline skeleton could still be 40 to 60% of your total project. That's okay. Anyone telling you that your end-to-end, that every sprint needs to have a fully working system has never actually worked on real software. But this approach, Brooks argues, necessitates top-down design, for it is top-down growing of the software. Common sense, if not common practice, dictates that one should begin system debugging only after the pieces work. Yes, unit tests, they're a thing. Architect your system top-down, but debug it bottom-up. That gives you the best end result. Now, I'm sure at this point that some of you, probably the same people who were complaining about waterfall earlier, are going to go, but Larry, didn't you just describe Agile? You've probably seen this screen before talking about Agile, of how this is a terrible way to make an MVP. You should totally do it this other way instead. Problem, this is terrible. This is a stupid summary. This is awful. When was the last time you managed to take a skateboard and turn it into a car? I never have. You don't. You throw it out and start over. What we see here is throwing the whole system away at least twice, because you can't go from a scooter to a bicycle or a motorcycle to a car. You start over. That's not an evolvable system. This is the big upfront rewrite. What you do instead is more like this. You start, bottom left here, with a skeleton that supports what your end goal is going to be. It's not a fully functioning car. That's fine. But it has wheels, it has an engine, it has a steering wheel. That's enough to get your working system. But it's a working system of the type you're going to want in the end. And then you can evolve it in place, add a trunk, change out the trunk, change the doors, change the colors, change out the tires. That's fine. But you're evolving it along the lines towards what you know you want, starting from an architecture and baseline and foundation that will lend itself towards that final goal. This also means you are not going to follow the standard Scrum practice of building the most user important feature first, because that's not actually the most important piece. If you're building a house and your client that you're building a house for tells you the most important attribute for this house for them is that I have a fireplace on the second floor bedroom, then a fireplace in the second floor bedroom is not the first thing you build. The first thing you build is the foundation. You pour concrete. Whether there's a basement or not, you start at the bottom. Because if you don't get that right, if you don't put in the time and effort to get a good solid foundation, it doesn't matter. You're not going to have a second floor to have a fireplace in. And even if you manage it, it's not going to make fire code. What do you think? Is this still true? Yep, this totally matches my experience. So I'm going to say Brooks is 2.5 for 3 at this point, because he did correct himself. In 1986, while receiving a prize at some conference, I forget which one, Brooks gave a paper called No Silver Bullet, which ended up as an extra chapter in the second edition of the book, in which he talks about the difference between essential complexity and accidental complexity. Essential complexity is the problem space itself is hard. If you've worked in e-commerce, why is e-commerce hard? It's not because the tools are lame. Some of them are, but that's not the real reason. It's because e-commerce is hard. Tax law is hard. Writing code that can handle shipping logistics is hard. This is just a fundamentally difficult problem space. Accidental complexity is the tools themselves are hard to use. Not that the problem space is complicated, but I'm using a tool that's not up to the task. And these are different types of problem that require different solutions. The hard part of building software is the specification, design, and testing of the conceptual construct, not the labor of representing it and testing the fidelity of the representation. Remember when Brooks was originally working, debugging was a process that involved picking up your stack of punch cards, walking down the hallway to the elevator, going downstairs to the basement, walking down the hall again to the room with the computer, handing your stack of punch cards to the computer operator, going back to your office, waiting 3 hours, coming back later and asking the operator what happened. The operator hands you a stack of cards and says, there was an error on card 427, have fun. Debugging by punch card is accidental complexity. It's very, very hard. Fortunately, we've moved past that. We now have real-time debuggers. We have languages that do memory checking for us. We have good type systems. We can do all of this work on our laptops while sitting on the beach. A lot of this accidental complexity that's not part of the core problem space is just gone. And it was already gone by the mid-'80s. There's no single development which by itself promises even one order of magnitude improvement in productivity, reliability, or simplicity. There's room for improvement, sure. We have gotten more productive since the 80s. We do have better tools now, better languages, but nothing on a scale that we saw in the early decades. The low-hanging fruit has already been solved. Most of the accidental complexity has been removed, which means what's left is essential complexity. So how do we resolve that? Well, Brooks offers a couple of options. One is rapidly prototyping and grow your system organically based on user feedback. We already talked about that in the last section, so I won't go into that more. He also suggests buy versus build and mentoring better architects. And there's a subtle language shift he starts using here of architect. Let's talk about buy versus build. The most radical possible solution for constructing software is not to construct it at all. Remember, in the 60s, computer hardware could easily cost $20 million for a single computer. That meant spending $50,000 to write custom software for it exactly to your needs. That's a rounding error in your budget. Your accountant won't even notice. These days, you can get a functional computer that is more powerful than half of what NASA uses for 10 bucks. And it comes with memory and everything built in. You just plug in a video card and a video cable, and a keyboard, and you're good to go. I have one. Hardware is not the cost center anymore. It's not that software is getting more expensive. It's that hardware has gotten so cheap, we now notice the cost of software. So how do we get more efficient and more cost effective at writing software? By not writing software, by reusing existing tools and components off the shelf that already exist so that we don't have to spend the time writing new ones. Who in their right mind is going to write a new spreadsheet from scratch these days? You're not. Who's going to write a brand new web server from scratch? There's really little point to. Most of these problems are much more easily solved by just pulling components off the shelf that already exist. You can download them on GitHub. Now, Brooks didn't use the term, but he just described open source. That's kind of the point. Don't write software, reuse software. Build an ecosystem where you can share and reuse modular components rather than having to custom write everything yourself and do a worse job than what's already out there. This is the #1 productivity improvement in the past 20, 30 years. If your code base, if your application, if your business is not 80% or more free software and open source, you are wasting money. You are just, might as well set it on fire. It'll do as much good for you. Most of your system should be open source these days, because that is how you write efficient code. That is how you become more productive. The way to be more productive is to write less code. The way to do that is to reuse more code. Brooks also says we need to grow great designers. Key change in name here, designer. Software construction is fundamentally a creative process. Study after study shows that the very best designers produce structures that are faster, smaller, simpler, cleaner, and produced with less effort. The difference between the great and the average approaches an order of magnitude. Oh my God, 10x developer, but prejudice, no. 10x designer. A great developer is not going to produce lines of code 10 times faster than a mid-level developer. But a great designer will design a system that requires 10 times less code to be written in the first place and is structurally incapable of having 10 times as many bugs. Software architecture is a separate discipline from coding, from engineering. It is a separate skill, and it's much closer to graphic design or usability engineering than it is to programming. And it needs, Brooks argues, equal recognition with management. Senior level architects are not people managers. It is a different skill set, but you need both, and both need to have equal recognition. If your business track, your promotion track at your company has engineer, 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 manager, 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 then you're telling people you have to be both a people manager and a code designer at the same time, which are totally different skills in order to advance. That's a great way to make sure you have mediocre architecture or mediocre managers, or probably both. They are separate responsibilities that are equal in stature, or should be. The way to get them is through mentoring. Identify candidates early who are potentially good architects. They may not be the most experienced developers. They may not be your best developers. They should be competent developers, but architecture and design is a fundamentally different skill than algorithm optimization. They are different skill sets, and that's okay. Assign that person a career mentor. Give them a explicit guidance to become an even better architect. Give them apprenticeships. Give them formal education. Let them take courses. Have them do solo work to practice designing code, not just writing code, but designing the system in which code lives. Encourage collaboration with other designers. Send them to conferences like this one, whether they're online or in person, so that they can work with and learn from others who are doing that skill, which is different than programming. These are all things that the design world does. we in the tech world need to do, because system architecture, system design is a creative design field, not an engineering field. What do you think? Is he right? Oh yeah, this absolutely fits with my experience. I say this as someone who is honestly a better architect than developer. I'm a good developer, but there are plenty of developers who are better than I am. I'm a much better conceptual architect than I am a developer. And finally, let's talk about conceptual integrity. Brooks argues that conceptual integrity of the product as perceived by the user is the most important factor in ease of use. As perceived by the user. Why? Because we want the user to have one mental model. We want the user to have only one set of nouns in their brain at once that they have to think about. They should not have to reconceptualize the world depending on what part of the products they're using. In fact, Brooks says ease of use is the relationship between functionality and conceptual complexity. It is not a straight linear number. It's how much functionality you get for how much you have to learn. Neither of these alone defines a good design. As an example, 3D modeling software. Have you seen what comes out of Hollywood these days? It's phenomenal. Most of it is animated. Most action films these days are computer generated, that they're an animated film. And 3D modeling software can take years to learn to use well. You need to take classes in it in order to use it well. But what you can do with it is phenomenal. At the other end of the spectrum, look at your text editor, look at Windows Notepad. Tiny, tiny functionality, and it takes about 14 seconds to learn because there's so little to do. Wait, did I just say that 3D Studio Max and Windows Notepad are equally easy to use? Yeah, kinda. Because they're easy to use relative to what they let you do. Simplicity and straightforwardness proceed from conceptual integrity. Conceptual integrity, Brooks argues, is the most important consideration in system design. It is more important to have a consistent design than more features. See also the original iPhone. The iPhone 1 launched with no copy and paste, no app store, mediocre data speeds. But the few things it did really, really well, and it sold like hotcakes. Having fewer features that work really well together makes it for a better tool than the Swiss Army knife of doom. But also, conceptual integrity of the product not only makes it easier to use, it also makes it easier to build and less subject to bugs. Because that one set of nouns concept applies just as much to the developer as it does to the user. If the architecture and the language is consistent, that means the developer can fit more of it in their brain at the same time and thus understand what they're doing. They don't have to translate, oh, it's called this over here, it's called that over here it's called a user, over here it's called an account, and so on. If you've heard the phrase ubiquitous language from the domain-driven design people, same basic idea. You want a very clear, consistent, big picture throughout the entire system. So how do you get that? Brooks argues it is through smart division of labor. The design must proceed from one mind or a very small number of agreeing resonant minds. You don't want design by committee, also known as emergent architecture, if anyone has heard that phrase, is how you get a big ball of mud. And Brooks has a couple of ways he suggests going about this. One is a surgical team in which the builder is focused specifically on writing the code. You have someone writing the code and nothing else, and everything is in their brain. And you have, it's just like in a surgical ward. You have a doctor standing over a patient operating, and she's focused, laser focused on whatever she's trying to cut so she can cut it properly. And there's another person over here who's handing her tools, another person over here who's wiping sweat off her brow, another person over here who's keeping the family away so that the doctor can focus. Same idea for a surgical team in software. I've never actually seen this happen. I've never actually seen it work. So let's not do that. The alternative is to split the role of architect and implementer, not to create a monothink, but to avoid conflict think. Because the mindset of the architect is different than the mindset of the implementer. The architect is the user's agent. It is their job to bring professional and technical knowledge to bear in the unalloyed interest of the user, as opposed to the interest of the salesman, fabricator, or whoever. They are a designer. They are a user advocate. They are a user experience person. That is what you want designing your architecture, designing your system. But Larry, this is cathedral design. We know that the Bazaar merchant design is better. This is open source. We all know that. Cathedrals are still standing after 800 years. Is your code still standing after 800 years? Bazaars, they're cheap, but they're not reliable. If you want something that will stand the test of time, that requires consistent picture. You can't build an 800-foot or 1,000-foot tall building emergently. That doesn't happen. See also, Apple. Until recently, Apple had a lot of designers, a lot of good designers, a lot of good architects, but at the end of the day, Johnny Ives is the one calling the shots. The vision of Apple's products is Johnny Ives, just Johnny Ives. For Google, they got a lot of great designers, they've got a lot of people working on a lot of different products, but at the end of the day, the overall look and feel and branding and concept behind their products is Matthias Duarte. Everything flows from Matthias Duarte. It is his vision that drives the visual look and feel and experience of any Google product. If you're working on any kind of Unix system, Linux, Mac OS, basically anything other than Windows, guess what? You're following the POSIX standard. Is that an ideal standard? That's irrelevant. That's the standard. That's how you interoperate. That's how things are designed to work together. If you work on the web, you're using HTTP. HTTP has a very robust set of architecture built into it. Are you ignoring its functionality? Guess what? You're doing it wrong. Are you trying to do caching some other way than how HTTP is designed to do caching? You're doing it wrong. You are going against the architecture. Yes, it's sometimes not nice to use someone else's architecture. We'd love to define our own. That's too bad. Swallow your ego. The web works this way. This is the way the tools are designed to work. Trying to fight the tool will create a mess. Will create more work than just going with the architecture and following the design that's already there. Yes, it's a central design. That's a good thing. An architect designs a watch dial with hands, that concept. The implementer is the one responsible for then building gears and bells. Both of these can be challenging. Both of these can be a lot of fun, but they are different things. A good architecture supports many different implementations. For those few people still using a wristwatch with a mechanical wristwatch, it is the same basic architecture as Big Ben in London, but it's very different challenges for the implementer. That's okay. The architect, however, must be prepared to show an implementation for any feature they describe, but not attempt to dictate the implementation. The architect does have a responsibility to demonstrate, I'm not asking you to do something impossible. I'm asking you to just do something that is in fact viable and possible to do. I'm not sending you on a wild goose chase. But once it's demonstrated that it is possible, the implementer gets to figure out what the best way is within the confines of that overall architecture. This requires ongoing, cooperative, high communication. This requires lots of talk. This is not, architect from on high, drop something on your desk and walk away. That doesn't work either. Another benefit of this is it reduces communication channels. You don't have to have all 15 people on the team talking to figure out what the architecture is. They all talk to just the one architect who is getting feedback and listening to ideas totally, and not just running off and dictating from on high. But at the end of the day, the architect is calling the shots. The architect decides what the approach is going to be and is responsible for making sure it is consistent. You can also divide and conquer this way. Take the system, break it up into smaller pieces. Each individual piece has a sub-architect responsible for it. The architects coordinate and then they manage their own individual component teams. That also can work really well. That's how the Linux kernel is managed, with a series of maintainers at different levels, and they talk to each other. You don't talk to Linus most of the time. Democratic architecture produces a big ball of mud every single time. You need a clear, consistent, leader-led vision of the architecture. That said, can we think of any projects that don't have very clear leadership and don't have a clear architectural vision, and therefore end up as kind of an inconsistent mess that you can use, but people always rag on because it's so inconsistent? You know any? There's about 100 different logos I could put here. This is the one that I like to make fun of because I work on it. What can we learn from this? Of course, we're talking about big systems here, large scale systems. How big is big before the things we're talking about here become relevant? After teaching a software engineering lab more than 20 times, I came to insist that student teams as small as 4 people choose a manager and separate architect. 4. Manager, architect, 2 implementers. Even at that small scale, you still need to split up your responsibility. Now, either the manager or the architect could be the final boss. Either one of them could be the one who's ultimately in charge. As long as everyone is on the same page as to which one it is, that's fine. But those are distinct roles. Manager, implementer, and architect are distinct roles, distinct mindsets, distinct skill sets, and most people are not going to be good at all 3. Most people are not good at 2. So what should we learn from all of this? First, software construction is a creative process. It has much more in common with graphic design and usability engineering than it does with engineering, with programming. Divide and conquer. This is your go-to strategy for any architecture or code. Take a complex problem, break it down into simple problems, solve those, stick those back together. That's how any science works. If you want to produce code effectively, you take that divide and conquer approach and use it to produce shareable programming system products. And you release them as open source. You leverage open source. You do not reinvent the wheel unless you have to. Use the off-the-shelf components. If you are not using primarily open source in your system, you are wasting money. To make this easier, decouple your libraries from the framework. If you can make your door fit on multiple cars, great. That makes it easier to swap out your A-frame in the car later. Cars don't use A-frames anymore, but you get the idea. To do this, you need to use top-down design. Figure out what it is you're actually trying to build. Don't just throw code at a wall until it gets there. Figure out what your big picture looks like and break it down into components from there. That gives you more swim lanes too. And finally, empower architects to make decisions. You need to have people who are in charge, who can make decisions, have them stick, maintain a consistent, coherent vision across your system. If you do not have that, if you do not have people who have both the responsibility and authority to decide on a direction, you will end up with a big ball of mud. Someone needs to be the gatekeeper. I'm going to use that word, yes, the gatekeeper for the architecture. They're the defender of the conceptual integrity of the system, and that is the architect's job. The architect's job is to say no, or to say this instead. That's how you get a system that can last and survive and grow and be comprehensible. The idea that people knew a thing or two in the 70s is strange to a lot of young programmers. From the father of analysis of algorithms and author of The Art of Computer Programming, Donald Knuth. What can we learn from this? Thank you for your time.